Hello everyone. Today I'm going to start a series of videos in which I'll talk about different types of polynomial series for functions like Taylor series, Maclaurin series, Fourier series. So this video is just an introductory video that tells you that why we need different types of series. All right, so did you ever wonder that how a calculator can give you the value of sine or cosine or cotangent of any angle? How can it give you the square root or cube root or fourth root or any nth root of any positive number? Or how can it find the log of any positive number that you give it? So, do you think that the calculators remember all the infinite numbers in this world possible, and then when you plug in the number, it instantly gives you that value? I'm afraid that's not true. So how does our calculators know what to do? So calculator just remembers special polynomials and substitute whatever you give it into that polynomial. So it keeps substituting into terms of that polynomial until it reaches the required number of decimal places. And then it displays the answer on the screen. So now the question arises, what are these special polynomials? Which special polynomials calculator remembers? So these are infinite series expansions, and today we will learn how to obtain such expansions using differentiation. So our aim is to find a polynomial that gives us good approximation to some function like sine x, cosine x, ln x, etc., etc. Since first we're going to start with the polynomials which are based on differentiation. So those are the Taylor series and Maclaurin series. So the study of these is largely about taking a non-polynomial function like sine x, cosine x, ln x, etc., etc., and finding the polynomial that approximate them near some point. So why do we need polynomials? Because polynomials are much easier to deal than other functions. They are easier to compute, easier to take derivative of, easier to integrate. So that's why we approximate the non-polynomial functions with the polynomial. Let's take a feel of what a function looks like in terms of a polynomial. So for cosine x, so if we take a look at this graph and this table, so the exact function is cosine x. So if you take the first approximation, it's approximated by this y equals to 1. So if we take the second approximation, 1 minus half x square, so we notice that so it's approximated by a parabola. And if we take the third approximation, so we even further notice that our function is hugging the curve even more. So as we add more and more terms, so we see that we get a better and better approximation of cosine x. So cosine x can be written in terms of a series where we have some powers of x. So this is what we're going to do in the next video. So we're going to learn how to find such a polynomial, how to create such a polynomial. But before we do that, so let's quickly go through some terminology that what does a series mean? What does a polynomial mean? All right, so now I'm going to go through some preliminary definitions that we already know, but I just want to remind in case you forgot. So first of all, we're going to talk about finite series. So what is a finite series? A finite series is the sum of finite number of terms. The main important part is that it involves the sum of some terms, and if the terms are finite, so we say finite series. So the example can be, you can simply have the sum of some numbers, or you can have the sum of some functions. So this is our finite series, so each of them have 4 terms only. So next we have arithmetic series. So an arithmetic series is the one in which each number can be obtained from previous one by adding a fixed constant. For example, if I have something like 1 plus 3 plus 5 plus 7 plus 9. So what we do here is, so each previous term we add 2 and we get the next term. So 1 plus 2 is 3, 3 plus 2 is 5. So we add 2 to get each subsequent term. Or we can have another example like 3 plus 4.5 plus 6 plus 7.5 plus 9 and so on. So here we notice that we get each subsequent term by adding 1.5 in the previous term. Then we have another type of series which is called geometric series. So this series is the one in which each term we obtain by multiplying a fixed constant to the previous one. So for example, if you have something like, so 2 plus 4 plus 8 plus 16 plus 32. So what do we notice here? So 2 times 2 is 4, 4 times 2 is 8. So what we do, we multiply by 2 at each step, right? So we get each term by multiplying by 2 to the previous term. Similarly, you can say that something like 3 plus 15 over 7 plus 75 over 49. So here we multiply each term by 5 over 7 to get the next term. And all these terms are added together. So the sum of the terms is in a series. Next, we have infinite series. So as the name suggests, it's the sum of infinite number of terms. So for example, if we have half plus 1/4 plus 1/8 plus 1/16, and if we keep on going and we don't never stop, so what is this sum? So sum of this series, so based on this geometric shape, so you can see that half plus area is 1/4, 1/8, 1/16, and you keep on going infinite time. So the sum of all these terms is going to be equal to 1 in the end. Similarly, if we think about 1 over 2 plus 1 over 3 plus 1 over 4, so we have sum of many infinite terms, and although these terms get smaller and smaller, but if you add infinite of them, so in the end it's going to be a divergent series and you're going to get sum that's going to get really big in the end. So infinite power series. So this is the most important terminology that we need for our Maclaurin series or Taylor series. So infinite power series is an infinite sum of powers of x or x minus a. So sum of powers of x or x minus a where a is some constant. So the examples can be, so something like 1 plus x squared plus x cubed plus x4 and so on. So this is an infinite sum of powers of x. It doesn't need to be necessarily the powers of x. It can be something like 1 plus x minus 3 plus half x minus 3 square plus 1/6 x minus 3 cube, but still we involve the powers of the factor x minus a, right? So a is 3 in this case. Or it can be something like, so you can have fractional coefficients, or so basically you can have odd powers of x and so on, or maybe just the even powers of x or something like this. So all these are examples of powers of x. So this is, all these are infinite power series. So now, since we know the different terminology, in the next video I'll straight jump on to how to form a Maclaurin series and what is a Maclaurin series. So please do watch that video as well. Thanks for watching this video. See you later.